Let's continue chapter 10. So we're continuing our way through Phys 8 slides 10.pdf starting at slide 32. But I did recently reorder the deck of slides, so you want to reload the file if you had it downloaded already. So let's start by quickly revisiting free body diagrams in one dimension. So here's a familiar problem from a couple weeks ago. You push on a crate and the crate starts to move, but you do not. Draw a free body diagram for you and one for the crate, then use the diagrams and Newton's third law of motion to explain why the crate moves, but you don't. Okay, we have some possible answers, but I think you know the answer by now. So I'm going to push on the crate. So my pushing on the crate results in this line. So this is the contact force exerted by me on the crate. So that appears on the free body diagram for the crate, and it points to the right. If the crate is to my right. By the way, there is a Newton's third law complement to that force. So if I'm pushing on the crate to the right with a force of this length, then the crate must be pushing back on me with a force to the left, which is of the same length. So that's Newton's third law. But then, meanwhile, if I am not accelerating, so there are only two horizontal forces acting on me. One is the crate pushing me to the left with the same magnitude as I'm pushing it to the right. That's Newton's third law. Crate is pushing me to the left, and yet I am not accelerating. So that must mean somehow the frictional force, the floor pushing on me, must point to the right and must be exactly big enough somehow to cancel the contact force exerted by the crate on me. You might wonder, how does it know to be exactly that correct magnitude? So we'll think about that in a minute. But meanwhile, you say, okay, the crate does accelerate forward. So if the crate accelerates to the right, then this friction force exerted by the floor on the crate must be smaller than this contact force exerted by me on the crate. So we have four forces in this problem. The free body diagram for me shows two forces. There's the crate pushing back on me, and there's the floor pushing on me with friction. And then on the free body diagram for the crate, there is the contact force that I exert on the crate. That's sort of the first force that we talk about. And then there's the friction force of the floor pushing back on the crate. And it seems like this force is smaller than this contact force I'm exerting on the crate because the crate accelerates forward. So it must be that the vector sum of forces on the crate points in the direction the crate accelerates. And we're only talking so far about horizontal forces, so it might be interesting to add into this picture soon a picture of vertical forces also. So this is the explanation as such as we're able to make it so far. So we have four forces, and three out of these four forces are the same length, and it's worth considering why they're the same length. This force and this force are the same length by Newton's third law. So if I push to the right on the crate, then the crate pushes to the left on me. That's Newton's third law. And then this frictional force has the same length as this contact force because we know that I am not accelerating. So one interesting question is, how is it able to do that? So we'll try to figure that out in a moment. And then we have this fourth force, which must be shorter because you know the crate is accelerating forward. So this frictional force by the floor on the crate must be smaller. If the crate and I were both standing on an ice rink, then it seems clear that we would both start to move. We would move away from one another because these friction arrows would both be 0. So there would be no friction force by the floor on me, and there would be no friction force by the floor on the crate. So there would be only one force acting to the left on me and one force acting to the right on the crate, and we would accelerate away from one another, though you know that our center of mass would not accelerate. If the crate and I were both bolted to the floor, then it seems clear that neither I nor the crate would start to move. So the grip of the floor's friction on my feet must be greater in magnitude than the grip of the floor's friction on the crate. And then we'll say it's reasonable that the magnitude of the frictional force exerted by the floor on the crate is smaller than the frictional force exerted by the floor on me because the bottom of the crate is wood, let's say, while the soles of my shoes are rubber. Okay, so we're going to have somehow a stronger frictional contact between rubber and the floor than we have between wood and the floor. And we'll try to quantify that in a moment. So we should try to define friction a little bit more carefully. So friction is a force that opposes the relative motion of two parallel surfaces that are in contact with one another. For example, I have this little box of drill bits and I have this sheet of plywood, and it seems as if something is stopping them from sliding with respect to one another. So static friction prevents the surfaces from starting to slide if their relative speed is 0. So you can see here I have this box of drill bits, this yellow box, and I have this little white string, and I can pull on the string. And you can see that the string is taut, so I must be exerting some non-zero force on the end of the string. So then the other end of the string is exerting a non-zero force on the box, and yet the box is not accelerating. So it seems, oh, but you just saw it budge now. So if I pull hard enough, the box will accelerate, but if I just pull a little bit, it seems as if friction will oppose that motion. So because the surfaces right now are not moving with respect to one another, this is called static friction. There's 0 relative speed of the two surfaces. So friction somehow pulls however hard it needs to pull to preserve that state where the relative speed is 0, but there's some maximum after which static friction gives out. So if I pull harder than static friction is able to pull back, then the box does accelerate. Okay, so that is static friction, and we are going to quantify how hard static friction can pull before it gives up and lets go. The other kind of friction is kinetic friction, and that tends to slow the relative motion of two surfaces that are moving with respect to one another. If I give this box a little shove, it doesn't just continue forever the way it would if it were on an air hockey table or on an ice rink. It stops after a while. So it seems that once I create a non-zero relative velocity of these two surfaces, then some kind of friction is acting to reduce that relative speed of the two surfaces. And that is called kinetic friction. So if the two surfaces have a non-zero relative speed, then kinetic friction acts to try to reduce that relative speed down toward 0. And then once that relative speed equals 0, then static friction has a chance to take over. There's another way you can see static friction, which requires you to use your mind's eye a bit more. So if I increase the angle of this sheet of wood, then you can maybe imagine that a larger and larger component of the gravitational force is trying to push the box downhill. And eventually that component of the gravitational force becomes big enough that static friction lets go, and we will quantify that in a moment also. So we have these two surfaces in contact with one another, and the surfaces are parallel to each other, and if the relative speed of the two objects is 0, then static friction does whatever it can to prevent the surfaces from starting to slide with respect to one another, although there's some limit after which it is no longer able to do that. Meanwhile, if the surfaces are already moving with respect to one another, then kinetic friction does what it can to slow that relative motion of the two surfaces. So the force of static friction is, up to some limit, as large as it needs to be to prevent the two surfaces from starting to slip relative to one another. And my kind of crude mental model for that is you can imagine that the surface of the floor and the surface of the crate are kind of like little grooved surfaces. You know, you imagine like kind of the edge of a gear or a little tooth pattern. And you can imagine this little grooved pattern will prevent relative motion if you just try to push a little bit, but if you push hard enough, then you can get the crate and the floor to move past each other, you know, because you're pushing hard enough to kind of get over these little grooves. So that's just kind of a crude mental model, but I kind of imagine like some little pattern of grooves. So the force of static friction is, up to some limit, as large as it needs to be to prevent slipping from starting, but there's some maximum value that the frictional force cannot exceed, beyond which static friction basically lets go and the surfaces begin to slip. So you can see there's no slipping, and then if I go enough, you see then the surfaces start to slip. So this maximum value is given by the normal force times the coefficient of static friction. So the static frictional force cannot be bigger than, it must be less than or equal to this dimensionless coefficient, it's just a number, no units, times the normal force. And what in the world is the normal force? The normal force is the contact force exerted by the, let's say, by the floor on the crate in this case, and it's perpendicular to the floor. So this is why we postponed our quantitative discussion of friction until we started to talk about motion in 2 dimensions. In order to quantify friction, we can't just draw free body diagrams in 1 dimension. Now we have to start drawing them in 2 dimensions so we can talk about the forces perpendicular to the floor acting on the crate and acting on me. So let's do that now. So we know there are 2 additional forces acting on me that we have not yet put into this diagram. So there is a gravitational force. So the gravitational force exerted by Earth on me, and it points down, and it equals my mass times little g. And then there also is a contact force, which we're going to call the normal force. Okay, so this is the normal force exerted by the floor on me. And we call it the normal force because there actually are 2 contact forces in principle exerted by the floor on me. One is perpendicular to the floor, and normal is another word for perpendicular. So we call it the normal force because it's perpendicular to the surface of contact. The other is the frictional force exerted by the floor on me, which is parallel to the contact between me and the floor. The normal force is perpendicular or normal to the floor and to the surface of my shoes, which are in contact with the floor. And the frictional force, if there is one, is parallel to the surface of the floor and to the surface of my shoe, which is in contact with the floor. And we know that these 2 forces must be equal in magnitude because I'm not accelerating up or down. Since I'm not accelerating up or down, the normal force exerted by the floor on me must be just big enough to offset this gravitational force exerted by Earth on me. So there are many examples in physics of forces that are just big enough to oppose some other force or are just big enough to prevent some kind of motion. And this normal force that the floor exerts on you is one example of that. If I had a mass of 10 tons or 100 tons, the floor might fail and I would fall through the floor. And then this normal force exerted by the floor on me would no longer be large enough to prevent me from accelerating downward. But as long as the floor does not fail, then the floor will push upward on me as hard as it needs to prevent me from falling through the floor. So I do not accelerate through the floor. And so then this normal force upward that the floor exerts on me equals the gravitational force downward that Earth exerts on me. So this is an example of what we call in physics a force of constraint. It's a force whose magnitude takes on whatever value is needed to satisfy some constraint. In this case, the constraint is that I don't fall through the floor. Now, if we look at the free body diagram for the crate, we can draw the vertical forces acting on the crate. Now the crate might have a different weight from me, so the crate might even be more massive than I am. So we can draw this downward gravitational arrow. So here's the gravitational force exerted by Earth on the crate. And then here is the normal force exerted by the floor on the crate. And the crate, it is accelerating to the right, but it's not accelerating vertically. So it must be true that this normal force exactly balances this gravitational force so that the crate does not accelerate in the vertical direction. The crate is only accelerating in the horizontal direction. And we know that just by observation that the crate is not falling through the floor and it's not jumping up and down on the floor. It's just sliding to the right when I push on it. So we've now drawn a more complicated diagram, but we might not yet have really explained to your satisfaction why the crate slips and I do not. And in fact, it seems as if the way we've drawn things, I decided, well, what the heck, let's draw it so that the crate has a slightly bigger mass than I have. So the normal force between the floor and the crate is actually bigger than the normal force between the floor and me. But let's say I'm wearing rubber soled shoes, and the bottom of the crate is some kind of nice, smooth, polished wood. So what allows the frictional force exerted by the floor on the crate to let go when my push becomes too big is that this coefficient mu static, so it's the Greek letter mu, so this coefficient mu static, which when multiplied by the normal force gives the largest possible value of the static force of friction, is large for something with a good grip like rubber, and it's small for something with it's like very smooth and slippery, like say polished wood. And this coefficient actually depends not just on one surface, it depends on the two surfaces. So like you could have wood on wood, or you could have rubber on rubber, or rubber on wood, and so on. So this coefficient, mu static, depends on the two surfaces, and it often depends on the details of the smoothness or the kind of finish of the two surfaces. So once static friction lets go, kinetic friction takes over as the surfaces are slipping past one another. So the way that works, so here's static friction preventing any motion from starting, but then eventually the required force of static friction is bigger than the maximum that static friction can provide, and the surfaces start sliding. Once the surfaces start sliding, then you have this much more easy to quantify force of kinetic friction. So let's see that happen. So we're going to, once they start to slip, okay, so once they actually are slipping, then you have kinetic friction rather than static friction. Kinetic friction is a little easier to quantify. Instead of this less than or equal to, where you have to evaluate how big a force do I need to prevent acceleration from happening, instead, kinetic friction just equals the coefficient of kinetic friction times the normal force. So as long as the surfaces are actually slipping past one another, then if you know the normal force and if you know the coefficient, then you can figure out how big kinetic friction is. And it points in whatever direction would tend to slow the relative motion of the two surfaces past each other. So since there actually is acceleration happening in this picture, it seems that in this case, since motion has already begun to happen, this must be the force of kinetic friction by the floor on the crate. If I gently step on my car's accelerator pedal and the car starts to move faster without any screeching sounds, the frictional force between the road and the rubber tire surface that causes my car to accelerate is it static friction, kinetic friction? Is it the normal force? Is it the gravitational force? Or maybe there is no frictional force. Well, on the one hand, I don't hear any screeching sounds. So that would seem to imply that it's static friction, but you might wonder, well, isn't the car moving? Doesn't that count as relative motion? So we have this important term in physics called rolling without slipping. And that is, if you have a wheel which is traveling on the ground and the wheel is rolling on the ground in such a way that there's no screeching sound, then the instantaneous point of contact between the tire and the road actually is not moving with respect to the road. You see, so at the instant that like this black stripe passes the road, there's no slipping between the road and the tire. So if I do this instead, then the tire is slipping across the road. But if I let the tire roll without slipping, then there's no relative motion between the tire and the road. So you kind of know, you can imagine your bicycle tire, and you can imagine that you're going kind of across the sidewalk. And in one case, you're going across the sidewalk kind of the way you normally would with your bicycle, and the wheels are rolling, and then you're not really wearing down the tires. And then imagine instead that you grab onto the brakes and you drag your bicycle across the sidewalk with your hand on the brake with the wheels locked. Then you're going to wear down the tire, and you're going to hear a kind of scuffing sound between the tire and the sidewalk. So that second case, where you're kind of dragging the tire across the sidewalk, is kinetic friction. So like wears down the surface. You can usually hear the contact between the surface and between the two surfaces, between the tire and the sidewalk. Whereas when something rolls without slipping, it's usually very quiet, and there's usually very minimal wear to the surfaces. And if you look really carefully, instantaneously at the point where the tire meets the sidewalk, there is no relative speed between that point on the tire and that point on the sidewalk. So if you have a wheel rolling down across the sidewalk, then if you just mark one little spot on the wheel in red, then you'll see that that one little spot on the wheel, if you trace out its motion, it takes this mathematical curve called a cycloid. And you see at the instant when that little red spot is at the bottom of the wheel, that it goes from moving directly downward to moving directly upward. So there's actually no back and forth motion between that spot and the sidewalk. So, and then that's true an instant later for another spot, and an instant later for another spot. So the instantaneous point of contact between the wheel and the road is not moving parallel to the road if the wheel rolls without slipping. So in fact, the force which is causing my car to speed up as I gently step on the accelerator pedal is static friction between the street and my car. So if we draw a free body diagram for my car at that moment, there is a downward force of gravity exerted by Earth on my car, and then there is an upward normal force exerted by the road on my car. That's perpendicular to the surface of the road, so it's called the normal force. And these two are equal to one another because the car, if it accelerates, it'll accelerate forward, not up and down. It's not going to jump up and down. And then there must be a frictional force. This is the force of static friction exerted by the road on my car. So we can use an S for static friction. We have an N for normal force, and we have G for gravitational force. So this is Earth is exerting a downward gravitational force on my car. The road is exerting an upward normal force on my car, and it's perpendicular to the road surface, so normal to the road surface. Normal means perpendicular. And then, in this case, friction, static friction is exerting a forward force on my car. So this is, the road is exerting a force in the forward direction on my car. It's the force of static friction. And there's no slipping, so you don't hear that like squealing sound you would hear from jamming on the brakes or from stepping on the accelerator so hard that the wheels slip. Instead, as the wheel moves around, the car moves forward. So if you imagine each time the car wheel turns around one complete revolution, the car moves forward by one circumference of the car tire. So that's rolling without slipping. So it is, in fact, static friction that accelerates your car forward when you accelerate gently and the wheels do not slip. So if instead I slam down on my car's accelerator pedal and the car screeches forward noisily like a drag race car, now the frictional force between the road and the rubber tire surface that causes my car to accelerate is, in fact, kinetic friction. You can hear that, and then, so you can kind of imagine I jam on the accelerator pedal, my car tire screeches forward. Maybe initially the car doesn't start to, and then the car moves forward, but the tire moves around. Each time the tire rolls around one complete revolution, the car goes forward less than one circumference of the tire because the tire is slipping and it's screeching as it goes forward. So you could imagine the car, so in the earlier situation, we had the car tire rolling without slipping. So every time the car tire goes around one complete revolution, the car goes forward one circumference of the car tire. Instead, in this case, we stepped on the gas pedal so hard that initially the tire is just spinning and spinning and spinning, and maybe the car is accelerating, but it's accelerating in such a way that if the tire goes around one complete revolution, the car is going forward less than one circumference because there's some relative slipping between the surface of the bottom of the tire and the road, and you can hear that, and you can also notice it in how quickly the tires wear down. So in that case, the force that's propelling my car forward is kinetic friction with a K instead of static friction with an S. And it almost always turns out that the maximum possible value of static friction is bigger than kinetic friction for a given two surfaces. So you usually get a better acceleration if you prevent the car tires from slipping. If you could accelerate smoothly enough that the car tires do not slip, then that usually gives you the optimal acceleration, because the possible frictional force between the road and your tires is bigger if the car tires are not slipping. In other words, the maximum possible value of static friction is almost always bigger than the kinetic friction value for the same two surfaces. Why do modern cars have anti-lock brakes? I'll get some possible answers here. Maybe the pumping action of the anti-lock brake mechanism keeps the brake pads from getting too hot. Maybe pulsing the brakes on and off induces kinetic friction, which is preferable to static friction. Maybe the weird pulsating sensation you feel when the anti-lock brakes engage is fun and surprising. It certainly is surprising. I think maybe I like answer C, because the coefficient of static friction is larger than the coefficient of kinetic friction. So you stop faster if your wheels roll on the ground than you would if your wheels were skidding on the ground. So it almost always turns out for a given pair of surfaces, like rubber on asphalt, that mu static, the coefficient of static friction, is bigger than mu kinetic. This is the coefficient of static friction, this is the coefficient of kinetic friction. Usually mu static is bigger than mu kinetic. And that means that the maximum possible value of F static is larger than the value of F kinetic. Remember, F kinetic equals mu kinetic times the normal force. F static is smaller than or equal to mu static times the normal force. So the largest possible value of static friction is where this inequality is an equal sign. And the normal force is the same in both cases. So if mu static is bigger than mu kinetic, then you can get a bigger stopping force. You can get a stronger frictional contact between the road and your tires, thereby slowing your car down more quickly if you're using static friction, thereby using this larger static coefficient of friction, which is possible if you have the wheels rolling without slipping. So you want to slow down as quickly as you possibly can without letting the wheels slip. So the car somehow has to sense, how quickly can I slow down without letting the wheels slip? And if they start to slip, then it says, okay, I'm trying to slow down too quickly, so I have to let go and back off a little bit and then brake a little bit more gently than I was just a moment ago. So in the case where your car is slowing down to a stop, if your car's velocity is to the right and its acceleration is to the left, then this force slowing your car down to a stop is the force of static friction exerted by the road on your car. It's static friction if you do not hear that screeching sound. It's kinetic friction if you try to brake too hard and your cars start to slide, and then you kind of hear that screeching sound, and you know that your car wheels are sort of locked and sliding against the surface rather than rolling and slowing down. Here's a photo of the evidence of a car that had recently screeched to a halt. You don't see the car, you just see the tire tracks. I'll show you a clearer version of this in a minute. So on the left side, you're going to see the tire track. The direction of travel of the car would be upward in the left side of the photo, and the direction of travel of the car would be kind of northeast in the right side of the photo. So let's take a look at the photo more carefully. Okay, on the left side, you see you're kind of looking directly down the street. So the car that screeched to a halt must have passed in the direction you're looking. And you can see that the tire tracks have little gaps. So there's a black mark where the tires were slipping, and that's kinetic friction. But then there are little blank spots where you just see bare pavement and you do not see a tire track. And those blank spots correspond to spots where the tires were rolling without slipping. So it's really those blank spots where you do not see tire tracks that contribute the most to the car slowing down. So the tire starts to skid a little bit, and then the anti-lock brake system backs off a little bit on the brakes, and then it brakes as hard as it can until the car just starts to skid, and then it backs off again. So it's really those little bare spots where there's no black mark on the road, I think, where most of the deceleration of the car is happening, because that's where we have the static friction between the tire and the road. And if you look at the bottom, at the right-hand side, I guess, of the photo, you can see that the marks get closer and closer and closer as you move from left to right. And the car was moving from left to right in the lower photo. And this makes sense, I think, because the anti-lock brakes, if you've experienced your own car engaging its anti-lock brakes, they pulse at a constant frequency, so it's like a constant interval in time. But meanwhile, the car is slowing down. So the pulses of the anti-lock brakes correspond to a shorter and shorter and shorter distance as the car slows down. So it makes sense that the little gaps in the tire tracks get closer and closer together as the car slows to a halt. So to summarize a little bit, static friction and kinetic friction, and sometimes kinetic friction is confusingly called sliding friction. You want to avoid saying that. If something is sliding, that's kinetic friction, but you want to say kinetic because the letter K is different from the letter S. So you want to remember kinetic is if they're moving with respect to each other, and static is if they're not moving with respect to one another. So kinetic friction just equals the coefficient of kinetic friction times the normal force, whereas static friction is however big it needs to be to prevent the surfaces from moving with respect to one another, but it has a maximum value. So you say static friction is less than or equal to the coefficient of static friction times the normal force. F static is less than or equal to mu static times the normal force, whereas F kinetic equals mu kinetic times the normal force. So we have the normal component of a force, which means perpendicular to the surface, and we have the tangential component, which means parallel to the surface. So if we have two surfaces in contact, then the normal force would be along this axis. This is the normal axis, and the tangential part, or the parallel part, would be along this axis. So friction acts along this parallel axis, whereas the normal force acts along this perpendicular or normal axis. So static friction is an example of what physicists call a force of constraint. And if I understand the usage properly, engineers tend to call this a reaction force. These forces have the property that in most cases you don't know the magnitude of the force until you solve for the other forces in the problem. And then you impose the condition of some known acceleration. And normally the condition is that the acceleration equals 0. One exception for when you do know the magnitude of static friction is if you're told that static friction just barely holds on or just barely lets go, then that means that static friction just barely has its maximum possible value. And in that case, you say this less than or equals becomes an equal sign, because you're asking where is static friction right exactly approaching its maximum so that it then gets a little bit beyond that and lets go. And we'll see in a moment that that's very similar to asking, okay, as we increase this angle, a little bit more, a little bit more, a little bit more, at some point the friction just barely lets go. The angle is too big and static friction just lets go. So if you ask what exactly is that angle where that happens, that's one way to determine the value of mu static. Here's a table from our textbook listing a variety of coefficients of friction. So it always takes two materials. It's basically two different surfaces rubbing against each other to determine the friction coefficient. And we have mu static in the left column and mu kinetic in the right column. And just a few examples, like ice on ice, mu static is 0.1, mu kinetic is 0.03. Okay, so that's a really small coefficient. Rubber on concrete is kind of at the other end. So rubber on concrete is a very good contact. So mu static is between 1 and 4. Okay, so that's really big. Whereas mu kinetic is 0.8. And if you take wood on wood, the range for mu static is between 0.25 and 0.5. Mu kinetic is about 0.2. All of these things are kind of approximate. It's hard to be really precise with friction. but it kind of gives you a good idea. So ice on ice is very low friction, and rubber on concrete is very high friction, and then wood on wood is somewhere in between. And again, you can see that in almost every case, the static friction coefficient is bigger than the kinetic friction coefficient. So that tells you that once something begins to slide, it keeps sliding for a while. Here's an easier to read copy of that same table. A couple other things to notice from this table of friction coefficients. For steel on steel, the coefficient of kinetic friction is about 0.4, and for rubber on concrete, it's about 0.8. And actually, steel on steel, if the tracks are wet, if you think about a train being able to stop, it's even lower, it's about 0.1. So it could really take a train a while to skid to a stop. So I remember learning, never ever think you can beat a train across a grade crossing. Another thing to bear in mind is if you have a train on wet, slippery tracks with a coefficient of 0.1, if you start from 60 miles per hour, it can take about 360 meters to slide to a stop at mu equals 0.1 on level ground. Oh, I guess we could work that out now. Once we learn how to work out friction on an incline, which we'll do in a moment, we could work out that on a 6-degree slope at mu equals 0.1, it's actually not possible to stop. So you especially don't want to challenge a train if it's on wet tracks going downhill. Let's see if we can work out this point. So for mu equals 0.1 on level ground, so this would be like steel on wet tracks. So then we have mu kinetic is about 0.1. So let's say we have a train on wet tracks starting out at 60 miles per hour, which is about 27 meters per second. And you want to know how long does it take to come to a stop starting from 27 meters per second if you're sliding steel on wet steel. So that's about 0.1. Let's draw a free body diagram for the train. So we have the gravitational force by Earth on the train, which is just the weight of the train. We don't know what it is, but it will cancel out. And we have the normal force of the track on the train. And so since the train is on level ground and it's not accelerating vertically, then this normal force just equals mg. And then we have the kinetic friction force. So we know that the kinetic friction force equals the normal force times the coefficient of kinetic friction. So that the normal force is mg in this case, and then we have the coefficient of kinetic friction. So that's the only horizontal force, okay? And let's say that this is our x-axis pointing to the right. So we have the mass of the train times a sub x of the train. So it's accelerating to the left, that's in the minus x direction. So this would be minus mg times the coefficient of kinetic friction. So then you see the m cancels out, and we get a sub x equals mu kinetic g with a minus sign. So if mu kinetic is 0.1 here, then this would be minus 0.98 meters per second squared. And then we can use our favorite constant acceleration equation, b final squared equals b initial squared plus 2a sub x, x final minus x initial. And let's say we set x initial equal to 0, and let's say we set v final equal to 0, and we want to know what is x final when it stops. So then that gives us 0 equals v initial squared plus 2a sub x, x final, which gives us x final. So then plugging in numbers, x final is minus v initial squared divided by 2 times the acceleration in magnitude, which is 370 meters, putting in numbers. So if the train starts at 60 miles per hour, and if it's on wet tracks and you only have 0.1 coefficient of kinetic friction, it takes it about 370 meters to slide to a stop. Let's work through a similar example to the calculation we just went through. A car of mass 1,000 kilograms travels at a constant speed 20 meters per second on dry, level pavement. The friction coefficients are mu kinetic is 0.8 and mu static is 1.2. What is the normal force exerted by the road on the car? So we're told that the car is not accelerating. Even if it were accelerating forward or backward, it's not accelerating up and down. So the normal force is going to exactly balance the gravitational force. So this is the normal force exerted by the road on the car. So that's going to be the same mg. So the gravitational force by Earth on the car is the car's weight, mg. And then the normal force by the road on the car will, in this case, be just whatever is needed to balance gravity, since the car is certainly not accelerating vertically. I mean, if it were bouncing up and down a little bit because it went over a pothole, then the normal force would have to change a little bit to account for that acceleration. But so we're driving smoothly across the road, so the car is traveling at constant horizontal velocity and it's not bouncing up and down. So there's no vertical acceleration. So then the normal force just equals mg so that the forces vertically balance. So then the normal force exerted by the road on the car is just g times the mass of the car. So mg, F normal by the road on the car is mg, which is 1,000 kilograms times 9.8 newtons per kilogram, which is 9,800 newtons upward. Continuing the same scenario, constant speed, dry level pavement, cruise control engaged to maintain this speed. Friction coefficients are mu kinetic 0.8, mu static 1.2. Tires roll on the pavement without slipping. What is the frictional force exerted by the road on the car? Well, the car is moving at constant speed in a straight line, so there's no acceleration. And if we are ignoring air resistance, then we don't need any horizontal force whatsoever on the car. So I think the frictional force is 0. Now, if you say that there is a tiny little force backward from air drag, so we'll call this the air drag on the car, which would oppose its velocity. Let's suppose that the velocity is pointing to the right and the acceleration is 0. Then to compensate for the air drag, there would have to be a tiny force of static friction by the road on the car, just enough to compensate air drag. So if we're ignoring air resistance, then this force of friction is 0. If we're going to allow for a tiny bit of air drag, which is trying to slow the car down, then we have to have just enough of a forward force of static friction on the car by the road to compensate that. Aha, I think I like this. It points forward. It must have a magnitude smaller than mu static times F normal, and it has whatever value is needed to counteract air resistance. I think I like that. Now what's this less than 12,000 newtons piece? Well, you see, we know that F static has to be less than or equal to mu static times F normal. And we know F normal in this case equals mg. So that tells us that F static is less than or equal to mu static mg, which means it must be less than or equal to 1.2 times 9,800 newtons, which is about 12,000 newtons. Being a little more careful, I could have said less than or equal to 11,760 newtons if I used G as 9.8 instead of G as 10. Continuing the same scenario, but now the car starts out going at 20 meters per second on dry, level pavement. Suddenly the driver jams on the brakes, and they are not anti-lock brakes, and the car skids to a stop with its wheels locked. Skids to a stop with its wheels locked. You can imagine the screeching sound. So what kind of friction is that? That's kinetic friction. If the car is going to accelerate this way, then we have F kinetic, and F kinetic equals mu kinetic times F normal, and F normal is mg. So then that equals mu kinetic mg, which is, in this case we have mu kinetic is 0.8. So F kinetic is about 8,000 newtons, a little bit smaller. So I think the frictional force exerted by the road on the car is kinetic friction. So that equals mu kinetic times the normal force. So that's just about 8,000 newtons pointing backward. Since the car is moving forward, then kinetic friction will oppose the relative motion of the car and the road. So it's going to point backward. That's a frictional force by the road on the car. It's kinetic friction, and it's 7,840 newtons backward, so about 8,000 newtons backward. By the way, if you wanted to work out the acceleration, you know there's only one horizontal force acting on the car, and it points in the backward direction, and you know how big it is. So we could write Newton's second law on the x-axis. We'll let the x-axis point to the right. So ma sub x is minus F kinetic, which is minus mu kinetic mg. So that gives us a backward acceleration of 7.8 meters per second squared. Suppose that for rubber on dry concrete, mu kinetic is 0.8, mu static is 1.2, car of mass m traveling at initial speed v initial on a level road jams on its brakes and skids to a stop with its wheels locked. Skids to a stop with its wheels locked. So that tells you that the wheels are screeching across the road, so there is relative movement between the surface of the tire and the surface of the road. So what kind of friction is that? That's kinetic friction. How do I solve for the length of the skid marks? I guess we could use v final squared is v initial squared plus 2a sub x, and then we could say x final minus x initial. So let's say x final is L and x initial is 0. M a sub x is minus F kinetic. So the only horizontal force acting on the car is kinetic friction. And so this is mu kinetic times F normal. And F normal equals mg by the same reasoning we used on the previous slide. So there's minus mu kinetic. So then we have a sub x is minus mu kinetic times g. So we actually don't need to know what the mass of the car is. We have mu kinetic is 0.8. So this is minus 0.8 times little g. So that's pretty close to minus 8 meters per second squared. It'll be a little less if we use g as 9.8 instead of g is 10. So I think I like answer D, delta here. So the acceleration is minus 8 meters per second squared. Actually a tiny bit less if you use 9.8 instead of 10.0 for g. And I guess if we did the math solving, so v final is 0, you want to know where it stops. So we get that the length of the tire tracks, the length of the skid marks is v initial squared divided by 2 times the coefficient of kinetic friction times little g. Suppose for rubber tires on dry level pavement, the friction coefficients are mu kinetic is 0.8, mu static is 1.2. If you assume the forces between the ground and the tires are the same for all 4 tires, so maybe it's like 4-wheel drive car, what is the car's maximum possible acceleration for this combination of tires and pavement? Kinetic friction gives you mu kinetic times the normal force, and the normal force is mg, so that's mu kinetic mg. Static friction will give you some value which is no larger than, the largest it could possibly be is mu static F normal, which is mu static mg in this case, because the normal force just equals mg. So it seems like if we write down m times a equals the frictional force, then the best we can do with kinetic friction is mu kinetic times g. The best we can do with static friction is mu static times g. So this is 0.8 times g, and this is 1.2 times g. So it seems like static friction will do quite a bit better for us than kinetic friction, or it can anyway. So it seems like the best we can do with static friction is 1.2 g, which is about 12 meters per second squared. So I think I like answer E here, echo, 12 meters per second squared. This is another reason, by the way, that we like anti-lock brakes, is static friction can decelerate the car faster than kinetic friction can. How hard do you have to push a 1,000 kilogram car with all of its brakes on, all of its wheels on level ground? So the wheels are locked by the brakes. to get it to start to slide. And let's take mu static is 1.2 for rubber on dry pavement. Well, drawing a free body diagram for the car, so we have the normal force just equals the weight of the car, and so to balance the forces vertically. So F normal is mg. So then the force of static friction will do its best to oppose my push. So then this is A of the car is 0, and that works fine for as long as the required static friction is less than or equal to mu static times the normal force. In this case, mu static times the normal force is 11,760 newtons. You can call it 12,000 newtons. Once I push 12,000 newtons or harder, then the static friction lets go. It can't hold anymore, and the car will start to accelerate forward, and instead we'll get kinetic friction. So then the car will be actually accelerating this way. So if I'm pushing with a force less than 12,000 newtons, the car will just stay put. Once my push reaches 12,000 newtons, the car will start to slide because static friction can't hold on anymore. So 12,000 newtons is how hard I have to push to get the car starting to slide. That breaks the static friction. And then to keep the car sliding at constant speed, so now it started sliding, so now to keep it sliding at constant speed, then I only have to push hard enough to balance the kinetic friction. And in that case, okay, so the car momentarily accelerates as I break the static friction, and now I'm going to reduce my push a little bit. So my push now is just big enough to counteract the kinetic friction to keep it sliding at constant speed. So its acceleration is 0 once again. Now I just need to push hard enough to oppose the kinetic friction, which is mu kinetic times mg. So that's 7,840 newtons, or about 8,000 newtons. So see, how hard do you then have to push to keep the car sliding at constant speed? And take mu kinetic as 0.8. So I have to push now at 8,000 newtons to keep it sliding. So I have to push 12,000 newtons to get it going in the first place. And then once it's sliding, I can keep pushing at 8,000 newtons just to keep it sliding at constant speed. How far does your car slide on dry, level pavement? If you jam on the brakes from 60 miles per hour, let's assume you do not have anti-lock brakes. So you jam on the brakes, so your car screeches to a stop with the wheels locked using kinetic friction. Okay, kinetic friction. So then that's mu kinetic is 0.8 for dry rubber on dry pavement, let's say. So then we say, okay, the only horizontal force acting on the car is kinetic friction, and it acts in the minus x direction, let's say. And the normal force just balances the weight of the car. So we have the force of kinetic friction is mu kinetic times mg. So that gives us, using Newton's second law, the acceleration in the x direction is minus mu kinetic times g. Then we can use our favorite x final squared as vx initial. We can then use this equation and say the final speed is 0, and that gives us a stopping distance of 46 meters, which is what I got when I worked it out earlier. By the way, how long does it take you to stop? Well, you could say 27 meters per second, and slowing down at 8 meters per second squared, right? That's 0.8 g. It takes you about 3.5 seconds to stop, starting from 60 miles per hour on dry level pavement. Oh, then you can ask, well, could you do better if you have anti-lock brakes? So if you have anti-lock brakes so that the tires never skid, you won't do quite this well, but the best you can possibly do is the maximum static friction. So instead you have F static is less than or equal to mu static F normal, right? So then instead of mu kinetic is 1.8, let's say we have mu static is 1.2. It's an approximate, it's a decent guess for, mu static is 1.2, let's say, for rubber on dry pavement. So then instead of 0.8 g, we would instead get 1.2 g for the best we can possibly do. So the acceleration is about 1.5 times as big. So that means our stopping distance is about 2/3 what it was before. So instead of 45 meters, we get 30 meters. That makes sense because our acceleration is 1.5 times as big, so the stopping distance is about 2/3 as big. So then the time it takes to stop, instead of 27 meters per second divided by 8 meters per second squared, which was 0.8 g, instead we have 27 meters per second divided by 12 meters per second squared, which is 1.2 g, so that's about 2.2 seconds. So it's about 2/3 the time and about 2/3 the distance if you don't let your tires skid, or whatever the ratio of mu kinetic to mu static. So anti-lock brakes or good enough reflexes that you can kind of pull, tap the brakes so that your wheels don't skid, potentially can reduce the stopping time and the stopping distance by, well, using these numbers, looks like about 30% or so. So if you have anti-lock brakes, then this mu kinetic downstairs can become mu static, and you can probably stop in, let's say, roughly 2/3 the distance or 2/3 the time, preventing an accident potentially. Calculate the dot product C dot B minus A. So take B minus A and take the dot product of that difference with the vector C if A is given by 3, 2, B is given by 1, minus 1, and C is given by 2, 2, where, the x component, the y component. So I think the first thing we want to do is work out B minus A, which is 1, minus 1 minus 3, 2. So we'll take this x component minus this x component. That's 1 minus 3, so that's minus 2. Right? So 1 minus 3 is negative 2. And then minus 1 minus 2 is minus 3. Then we have the vector C is 2, 2. We want to take the dot product with this difference that we worked out down here, which is minus 2, minus 3. And so we want x component times x component and then plus y component times y component. So this is 2 times minus 2 plus 2 times minus 3, which is minus 4 plus minus 6, which is minus 10. So the answer is minus 10. A child rides her bike 1 block east and then square root of 3, which is about 1.73 blocks north to visit a friend. It takes her 10 minutes, which is 600 seconds, and each block is 60 meters long. What are the magnitude of her displacement, her average velocity, written as magnitude and direction, and her average speed? Okay, so it's a little diagram. She goes 1 block east and then square root of 3 blocks north. So her displacement is delta R, which is R final minus R initial, and that is in x, y notation. It is plus 1, plus square root of 3 blocks. And then if we want the magnitude of her displacement, that is the magnitude of this vector, which is the magnitude of this vector, and this is the square root of 1 squared plus square root of 3 squared blocks. So 1 squared is 1, square root of 3 squared is 3, so this is square root of 4 blocks, which is 2 blocks, which is 120 meters. Okay, so the magnitude of her displacement is 120 meters. Magnitude of her displacement is 120 meters. Her average velocity. So her average velocity is her displacement divided by the elapsed time, which is this vector plus 1, plus square root of 3 in vector form blocks, we could convert it to meters if we wanted to, divided by 10 minutes, which is 600 seconds. But now we actually want the magnitude of her average velocity. Well, the magnitude of her average velocity is the magnitude of this stuff, and we already worked out the magnitude of this numerator. So this is 120 meters divided by 600 seconds, which is 0.2 meters per second. So the magnitude of her average velocity is 0.2 meters per second. How about the direction of her average velocity? Well, the direction of her average velocity is going to be the same as the direction of her displacement. So actually, the direction of average velocity is the same as the direction of her displacement. The displacement, which usually we write delta r. And so this is root 3 north, 1 east. So if you look at this triangle, you take this angle theta, which is the direction of her displacement, then the tangent of that angle theta, which is the direction, which is how far north above east it is. It's like something vaguely northeast. The tangent is root 3 divided by 1, which is, okay, root 3. So arctan of root 3 is 60 degrees. So this is 60 degrees north of east. So the direction of this, so this theta is 60 degrees. So the direction of her displacement is 60 degrees north of east. What is her average speed? Well, her average speed is the distance traveled divided by the elapsed time. What is the distance traveled? It's 2.73 blocks, right? This is one block, that's 1.73 blocks. So this is 2.73 blocks divided by 600 seconds, which is 10 minutes. And then, so we're going to convert this into meters per second. So this is 2.73 blocks times 60 meters per block. And then we have divided by 600 seconds. And the 60 cancels the 600, leaving a factor of 10. So this is 0.27 meters per second is her average speed. So her average, the magnitude of her average velocity is 0.2 meters per second, whereas her average speed is 0.27 meters per second. And it makes sense that her average speed is bigger than the magnitude of her average velocity because she changed direction. And one thing that's more subtle about this than the chapter 1 problems is that she didn't change direction along a line, she changed direction in a plane. So then you have 2 dimensions to work with. And we had to use the Pythagorean theorem and some trigonometry.